Hi again, everybody. This is part one of a two-part review for the light unit. Let's start with the electromagnetic spectrum. So the electromagnetic spectrum sort of examines the type of radiation that we have discovered in science. We go from the low frequency radio waves to the high frequency gamma rays. And as you can see in this picture here, so this is one of the resources that you guys had in this electromagnetic spectrum lesson. You'll notice that the long wavelength radio waves have a low frequency, so large wavelength, low frequency. Whereas as we go across the spectrum to the really scary, dangerous stuff, the gamma radiation, we have small wavelengths, really high frequencies. Interesting things to note here, the visible light spectrum, the part of the light spectrum that we can see with our eyes, is a very small sliver of all of the light that exists. It's right in the middle. It's a tiny, tiny, tiny segment of the entire spectrum. Cell phone radiation is over here in the microwave range. That would be also, of course, microwave ovens use that kind of wavelength. Radio waves speak for themselves. Infrared, interestingly enough, so here this is kind of where we see the heat energy. So if you put your hand near a campfire, it's that infrared radiation that your hand is absorbing, warming up your hand. Ultraviolet, we know that in the summer, that's the type of radiation from the sun that causes sunburns and things like that. And usually anything ultraviolet or higher. So if we're over in this range right here, that's where we get ionizing radiations, high energy radiations. Of course, X-rays, gamma rays are in and of themselves dangerous to cells, and that has to do with the amount of energy that is associated with those types of radiations. So just to give you a quick recap of some of the takeaways, if we take a careful look here, our shortest, so let me add some notes here. So our shortest wavelength radiation, the smallest wavelengths are going to be there towards the gamma radiation side. Okay, and as far as the visible light spectrum goes, that very small sliver that we're able to detect with our eyes, what is that, 400 to 700 nanometers of wavelength, we would say the shortest wavelength of light on that front would be the violet light. Okay. Again, that's the part that we can detect with our eyes. As far as moving a little bit onto the other side of the story, the longest wavelength radiation would be the radio waves. Okay. There, in the news, there's this story about 5G signals coming for the new medium by which cell phones gather data. All of those microwave signals are below the energy of visible light. So if you have red light, green light, anything like that striking your skin, that's going to be a higher energy than something that's in the microwave range. Okay. So anyway, going into the longest wavelength, that would be in the visible spectrum, that would be red light. And red light, of course, in and of itself, would be among the Roy G. Biv colors that we can detect, would be the lowest energy, largest wavelength, lowest frequency color of light that our eyes can detect. Okay. Couple of questions. I'll just go through these verbally. Can electromagnetic waves travel in a vacuum? Yes, they can. Light doesn't require a medium. Sound waves do. Light waves do not. So they can travel through a medium, but they don't need it. So all of these radiations are good to go without a medium, such as air or water, things like that. Okay. Cell phones are in the microwave region. That's over here. Okay, so that's where the 4G, 5G signal stuff comes from. Again, just from a conceptual perspective, anything in the microwave region is lower energy than visible light. So if you're not afraid of getting a little bit of sunlight, white light is really just a composition of those fundamental frequencies, then you should be okay with microwave signals from your cell phone striking your skin. Um, let's see, what else can I talk about? Oh, the speed of light. So something to add to the notes here, just as a review, all light travels at about 3 times 10 to the 8th meters per second. So it's, for our purposes, that seems like an infinite number, but it's not infinitely fast. It's only three, what is that, 186,000 miles per second or something ridiculous like that. It's really, 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 really fast, but it's not infinitely fast. And this is true for radio waves. This is true for gamma rays. This is true for red light, yellow light, orange light, blue light. All of it travels at the speed of light. The symbol C is used because it's a constant. So no matter what frame of reference you're in, the speed of light is 3 times 10 to the 8th meters per second. We did a lab called the Speed of Light Lab. I'm just going to go through that here next, just to give you some feedback on that. So we had a candy bar in a microwave, and that microwave was 2,450 megahertz. And one thing that you can do is when you put the candy bar in the microwave and you don't let the microwave spin, you sort of let the candy bar sit there, you can sort of see where the candy bar melts. And in that particular case, let me draw a picture here. So this would be, okay, that would be sort of a transverse wave, which is the kind of a wave that light is, not to be confused with longitudinal waves. If we measure from here to here as 2.5 inches, that's where the candy bar melted. So if we carefully examine this, so from here to here is a wavelength. So if we turn 2.5 inches, which is half a wavelength, into a full wavelength, that means our wavelength is 5 inches. We can convert that into the centimeter, and then we can convert that into meters. All right, so give that a try if you didn't get this correct in the original experiment, but you end up getting 0.127 meters. There's 2.54 centimeters in 1 inch to do the conversion. So to find the speed of light from this lab, you can use the equation, the wave speed is equal to frequency times wavelength. Really, this is an application of displacement per unit time or distance per unit time for speed. And without getting into that, that's from a previous unit. We can sort of describe this with the following numbers, right? So that's 2,450 megahertz, so that's 2,450 times 10 to the 6th hertz. We don't want to use megahertz in this equation. And then wavelength is 0.127 meters, as I just mentioned a moment ago. And when you plug that together, you get 3.11 times 10 to the 8th meters per second. Remember, hertz is inverse seconds, which is a really nice way to experimentally determine the speed of light using microwaves. Okay. Last thing I'm going to talk about in this video is the Doppler effect and redshift. So what happens with waves, it could be sound waves, but light does this as well, is if the wave source is moving, or if the observer is moving, or if both are moving, what happens is those wave fronts can be compressed or spread apart. Depends on if the source is moving towards you or away from you. So if we can imagine we have, some red light coming off of a star or something, if that star is moving away from, so here we are, Earth, okay? If that star is moving away from us, okay, so here's the star, what's going to happen is the way we detect the signals from that star, so stars are going to give off radiations in pretty much the whole range in the spectrum. So stars are going to pump off radio waves, microwaves, ultraviolet, X-rays, gamma rays, visible light. That's the part that we see with our naked eye, right? So if it's a red star like Betelgeuse star out there, interesting stuff in the news about that recently. What happens is we can find out if that light that's detected here on Earth, is it behaving the same as light that we see in our experiments on the surface of the planet. And what happens is we get these emission spectra, and if those emission spectra are shifted towards the red side of the spectrum, we call that redshifted. That means the star must be moving away. Effectively, that's a Doppler effect. Okay, just like sound frequencies can change when the source is moving away from you or towards you. So, for example, a car goes by and it goes, right? On the way away from you, the pitch decreases. Well, the same thing can happen with light signal. As these wave fronts are detected by us, if the source is moving away from us, we're going to have that shift. Okay, in this case, redshift means the light source is moving away from you. Scientists have discovered redshift for stars in all directions. That's one of the reasons we know the universe is expanding. The Andromeda Galaxy is an aberration. That stars in the Andromeda Galaxy are actually blue shifted, meaning that that galaxy is moving closer to us over time. All right, so that's all I have for this video. Part 2 coming up soon. Let me know if you have any questions, and I'll see you again soon.